Hello students, today in this lecture we are going to cover the next two pending applications of the Gauss's law for electrostatics. In our last lecture we have covered the Gauss's law and its three applications. The first one that is related with the point charge, and second application related with the linear charge distribution, that is lambda is there in the final formula, and in the third application there is that is related with the surface charge distribution. And here in this application number 4, it is the electric field due to two infinite parallel charge sheets. Okay, the case of one charge sheet is taken in the application number 3 already, and there comes the result as the sigma by 2 epsilon naught. The electric field comes out to be sigma by 2 epsilon naught. What is sigma? That is surface charge density. Okay, and here in this case we are considering two parallel charge sheets. So there are two parallel charge sheets, sheet number A and sheet B. On the sheet A there is the positive charge, and on the sheet B there is the negative charge. Now let's consider there are 3 points. One, let us say point P. Here is the point Q, and here it is the point R. Okay, in the 3 different regions, like Q is in between the sheets, P is on the left side, and R is on the right side of the negative sheet. Now we know that the field lines are diverging for the positive charge and converging for the negative charge. So for the point P, if the electric field for the sheet A is E1 and for the sheet B is E2, let us say, then for the point P, so what is the direction? Like we know that for the positive charge, the field lines are diverging. So for the positive charge, the direction for E1 vector is this one. Okay, this is the direction for E1 vector, and what is the direction for E2? As the negative charge is there on the sheet B, so for E2 it is converging. Okay, it is towards the negative charge, so it comes out to be for E2. This is the direction for E2 vector. Okay, and similarly now at point Q, for positive charge it is away from the positive charge and towards the negative charge. So E2 again comes out to be, okay, E1 is for the positive charge and E2 is for the negative charge. For negative charge, it is towards the charge sheet, and for positive charge, it is away from the charge sheet. Okay, now at point R, so direction for E1 is again, this one is E1, and for E2, it is like this. Okay, so these are the directions for E1 and E2 vector at different locations P, Q, and R. And we know that the E is the for the single charge sheet, as we have derived in our last application. So it comes out to be E is equal to sigma by 2 epsilon naught. So what is sigma? Sigma is the surface charge density, epsilon naught is the permittivity, and E is the electric field intensity. Okay, so this is the formula that we have derived in our last application, that is the due to the single charge sheet. Now for the case of two parallel charge sheets, so here now at point P first. So at point P, what is the resultant electric field intensity? So it comes out to be resultant electric field intensity. As you have seen here across the point P, the direction of E1 and E2 are opposite to each other. Okay, so we can write it like this: E1 minus E2. Okay, and now just simply applying the formula for the surface charge distribution, that is sigma by 2 epsilon naught minus sigma by 2 epsilon naught, and it comes out to be 0. So this formula we have derived in our last application for the when the charge is distributed over the any sheet. Okay, now at point Q, at point Q, the resultant electric field intensity, as both are having the same direction. Okay, so the resultant comes out to be the simply the sum of E1 plus E2, and it is sigma by 2 epsilon naught plus sigma by 2 epsilon naught, and this comes out to be sigma by epsilon naught. Okay, so this is for at point Q. Now at point R, here the resultant electric field intensity, as seen here from the diagram, that the direction for E1 and E2 are again opposite to each other. So here also comes out to be E1 minus E2 and equals to sigma by 2 epsilon naught minus sigma by 2 epsilon naught equals to 0. So what does we conclude from these three results? Now let's see at point P, that is outside the parallel sheets. So it is 0. Okay. At point Q, that is within the parallel sheets, it is sigma by epsilon naught. And at point R, again outside the parallel sheets, it is again 0. So what does we conclude from these three results? So hence E, due to the two oppositely charged infinite plates, is sigma by epsilon naught at any point between the plates and is 0 for all the external points. Okay. So what is concluded from this small derivation, that the electric field intensity at anywhere within the plates, at any point in the plates, it is sigma by epsilon naught, whereas it is 0 at all the external points, whether it is on this side or on that side. Okay, for all the external points, the electric field intensity is 0, and for all the internal points, it is sigma by epsilon naught. So this is your application number 3. Now let's start with the fifth application, in which the charge is uniformly distributed over any volume, and that volume is taken in the form of sphere. Okay, so the fifth application is electric field due to uniformly charged sphere. And we know that when the charge is uniformly distributed over any volume, so that is represented by rho, which is the volume charge density. Okay, so for this application, let's consider a sphere. So this is the sphere with positive charge uniformly distributed over it. The radius of the sphere is capital R, and this dotted one is the Gaussian sphere, that is the imaginary Gaussian surface that is there on around this sphere, and the radius for that Gaussian sphere is smaller. So for doing this application, we have to consider three cases first. So in the first case, let us consider a small point P at an external point. Okay. So case 1, in the case 1, consider a small portion at any point P externally anywhere to the sphere. Not on the sphere, not in the sphere, it is any point P externally to that sphere. Okay, so let us see here any point P, and on this point, as it is a positive charge, so Direction for electric field vector is this. Okay, and the direction for ds vector is also this. Okay, so both E vector and the displacement vector are pointing outwards for any point outside the sphere. Okay, so this is our first case in which we are considering the any point outside. So just take it as first case at any external point. That is when R is greater than R. So this R is the for the any external point P when R is greater than R. So here we are considering a point P lies outside the charged sphere. Hence d phi comes out to be as we have done in our first application, that is due to the point charge. So here d phi, it is equals to E dot ds, and both are pointing outwards, so it comes out to be E ds cos of 0 degree, and cos of 0 degree is 1, so it comes out to be E ds. Okay, and the total flux now comes out to be, therefore this one is same as we have done in our first application. So the total flux phi, it is equal to d phi, or it is like this. And what is this? This is the surface area for the sphere. Okay, this one is the surface area for the sphere, and we know that it is E into 4 pi r square. And here you have to take small r because we are considering the point that is having the radius of r, small r. Okay, so it comes out to be E into 4 pi r square. 4 pi r square is the surface area of the sphere. And now according to Gauss's law, phi is equals to q by epsilon naught. Okay, one phi is this, second phi is this. Just mark them as equation number 1 and equation number 2. Now comparing 1 and 2, after comparing 1 and 2, so we are getting E into 4 pi r square is equals to q by epsilon naught. Okay, and from here, so this formula comes out to be E is equal to 1 by 4 pi epsilon naught into q by r square. Okay, so this is the electric field intensity for any point if considering at any external point. Okay, that is outside the charged sphere. If you consider any point outside anywhere in the Gaussian surface around the charged sphere, so the electric field intensity at that point due to this charged sphere comes out to be 1 by 4 pi epsilon naught q by r square. Q is the charge on that sphere. Now in the second case, case 2, here we are going to consider a point P on the surface of sphere. Okay, here in the second case, we are considering this point P on the surface of the sphere. Now let me change this. Now I am going to consider this point, let us say here. So on the surface of sphere, and for this case small r is equal to capital R. Okay, and if the point is here on this, on the surface of the sphere, so again the E vector is here and ds vector is also here. Okay, both are pointing outwards because of the positively charged sphere. So E vector and ds vector are outside, but here the condition is r is equal to, small r is equal to capital R. Okay, and here the formula comes out to be the same. So here also E comes out to be 1 by 4 pi epsilon naught Q by, but here you have replaced this small r with capital R. So it is R square. So this is the formula if you have to consider any point on the surface of the charged sphere. So it comes out to be 1 by 4 pi Q by R square, and this R is the radius of the sphere. Okay, this R is the radius of the sphere, equal to the radius of the sphere. Now case 3. Now in the case 3, we are going to consider any point within the sphere. Okay, any point within the sphere at an internal point. जैसे यहाँ लिखा था at any external point. So here I am going to write at any internal point. And here the case is small r is less than capital R. Okay, and now I am going to change it again, the point P. So now this is my main sphere with the radius R, and I have to take any point internally to this sphere. So I'm again drawing here another sphere, and the radius of this sphere is small r. Okay, and this complete radius of the actual sphere is capital R. Okay, and here small r is less than capital R. So here again, as E vector and ds vector are pointing outwards, if you have taken any point here, P point, and marking the vector, so E vector and ds vector are both pointing outwards due to the positive charge inside the sphere also. So here phi again comes out to be as we have done here. So phi is equals to, and finally written here, E into 4 pi r square. Here I am using the small r, 4 pi r square, because this flux is calculated at the point P. Okay, 4 pi r square. Now, as we know that the charge is uniformly distributed over the charge sphere. Okay, we know that it is actually a uniformly charged sphere. Okay, so charge is distributed evenly everywhere in the charge sphere. So the rho comes out to be rho. Therefore, rho is equals to volume divided by, rho is actually the volume charge density. So rho is equals to charge per unit volume. Okay, rho is charge per unit volume. And what is the charge? Charge is Q, and volume of the sphere now it is given as 4 by 3 pi r cube. It is 4 by 3 pi r cube. This is the volume of the sphere. Okay, this is the volume of the sphere. Now, but the volume of the Gaussian surface, volume of Gaussian surface is equal to, so now our Gaussian surface is internally to the actual sphere. So the volume of the Gaussian surface comes out to be 4 by 3 pi small r cube. Okay, this is the volume of the Gaussian surface, and this is the volume of the actual sphere. Okay, this is for the Gaussian surface, because in this case the Gaussian surface is internally to the actual sphere. Now the charge contained by the Gaussian surface. So What is the charge that is contained inside the Gaussian surface? So hence, therefore, charge in the Gaussian surface. Let us say that charge is Q1. So charge in the Gaussian surface, it is Q1, and this is equal to rho into volume. Okay, now what is rho? That is the volume charge density, this much. And so this is equal to, further equal to Q divided by 4 by 3 pi r cube, and the volume of the Gaussian surface is this much, that is 4 by 3 pi small r cube. Just cancel out this one and we came up with, it is Q r cube divided by capital R cube. Okay, this is the charge that is enclosed in the Gaussian surface. Okay, this is the charge that is enclosed in the Gaussian surface. Now, according to the Gauss's law, I'm just going to rub this first case now. Now, according to the Gauss's law, phi is equal to, now we have to apply the Gauss's law for this internal Gaussian surface. Okay, so it comes out to be Q1 divided by epsilon naught. Here you not have to take Q, it is Q1 by epsilon naught. Okay, so 1 and Q1 is our this much. Okay, this is Q1. So here comes out to be Q into R cube divided by R cube into 1 by epsilon naught. That is as per the Gauss's law. Okay, this is as per the Gauss's law. Now comparing this with this phi. Okay, now comparing one phi is this, that is E into 4 pi r square, and other phi is this much. Now comparing both, or you can mark them as number 3 and number 4. Now compare 3 and 4. Compare 3 and 4. This is your number 3 and this is your number 4. So as per number 3, it is E into 4 pi r square. So this is equal to 1 by epsilon naught q r cube divided by r cube. Okay, and just cancel out, here it is r square and here it is r cube. So this cancel out and we are left with, so finally E comes out to be 1 by 4 pi epsilon naught q r by r cube. Okay, so this is your final result for this fifth application, that is electric field due to uniformly charged sphere. So in this application, we have considered 3 cases. In the first case, we have taken any point that is outside the charge sphere. And for that case, the result comes out to be the same that we have found out in case of our first application, that is 1 by 4 pi epsilon naught q by r square. So this is the formula for the electric field intensity for any point considering outside the sphere. And if in the second case, we have considered that point on the surface of the sphere. And for that condition, so E vector comes out to be 1 by 4 pi epsilon naught q by r square, and here r is the radius of the sphere. Okay, and in the third case, we have considered any point internal point, that is internally into the sphere. And for that case, the final answer comes out to be E is equal to 1 by 4 pi epsilon naught QR by RQ. Here capital R is the radius of the sphere and small r is the radius of the Gaussian surface everywhere. Okay, whether it is a case 1, case 2 or case 3, capital R is the radius of the sphere and small r is the radius of the Gaussian surface. In the first case, Gaussian surface is outside. In the second case, Gaussian surface is on the surface of the sphere. And in the third case, the Gaussian surface is internally taken. Okay, so these are the three results for this fifth application, that is the case of volume charge distribution. So overall, we have covered 5 applications. One with the point charge, second with the linear distribution of charge, third with the surface charge distribution, fourth with two parallel sheets, charge distributed over two parallel sheets, and finally the fifth one when the charge for the case of uniformly charged sphere, that is for the case of volume charge density. Okay, so these are the complete 5 applications for the Gauss's law. Now let's start with the next topic, that is the Gauss's law in differential form, or it is also called as the point form of Gauss's law. And just read the definition. It states that the divergence of electric field E vector, okay, it's a divergence of electric field E vector at any point in space is equal to 1 upon epsilon naught times the volume charge density rho at that point. Okay, so mathematically it can be written as del dot E vector because the divergence is represented by the dot product with the del. Okay, del dot E vector is equal to rho by epsilon naught. Rho is here the volume charge density and epsilon naught is the permittivity. Okay, so this is the definition for the point form of Gauss's law. Now let's start with proof. So starting with the proof, now let's consider a small volume dV enclosed by the surface ds. Okay, so considering for this, there is a small volume dV enclosed by the small surface ds. Consider small volume dV enclosed by surface ds. Okay, then according to the Gauss's law, for the continuous charge distribution, now according to Gauss's law, for continuous charge distribution, so it is equal to E ds is equal to rho dV. Here is the surface integral of E vector. So this is equal to 1 upon epsilon naught times rho dV. That is the for the charge, because here the charge is continuously distributed over the volume, so it can be represented as rho dV by epsilon naught. Actually, this is equal to phi, electric flux. Okay. So this is as per the Gauss's law, and just mark this as equation number 1. And just put here volume integral and here it is the surface integral. Now, according to the Gauss divergence theorem, or applying Gauss divergence theorem to the left hand side. Okay. Now, apply Gauss divergence theorem on LHS. Left hand side here. So this can be written as E ds. So as per the Gauss divergence theorem, the surface integral is converted into the volume integral. So this comes out to be equal to the volume integral of del dot E. dV by the Gauss divergence theorem. Now mark it as equation number 2. Now in the next step, compare 1 and 2. Just compare these two equations. Compare 1 and 2. And when you compare this with this, you come out with, that is actually volume integral of del dot E dV is equal to 1 by epsilon naught, the volume integral of rho d. Okay, and you can also write it like del dot E vector minus rho by epsilon naught dV equals to 0, and can further be written as del dot E vector minus rho by epsilon naught is equal to 0 because the volume is arbitrary. Okay, so that's why it is equal to 0, and from this you got this as final result, hence proved. Okay, so this is the complete proof for the Gauss's law. Hence proved. Okay, so this is a small derivation for the point form of Gauss's law. And there is one limitation for the Gauss's law, that the Gauss's law cannot be applied on the non-Gaussian surfaces. Okay, so for the Gauss's law, the Gaussian surface must be there. Gauss's law cannot be applied for the non-Gaussian surfaces. Okay, so what does this mean? That it can be applied only if the surface encloses the volume completely. Okay, so the condition for the Gauss's law to be applied, that it can be applied only if the surface encloses the volume. That is the same condition that we have taken in case of our Gauss divergence theorem also. Okay, so this is the limitation for the Gauss's law. One thing, it cannot be applied on the non-Gaussian surface, and secondly, it can be applied only when the surface completely encloses the volume. Okay, so this is all about the Gauss's law, their applications and its point form, and then its limitation. Okay, so this is complete about the Gauss's law.